Hello, everyone. My name is Peter Hase, and I'll be talking with you today about our paper on the out-of-distribution problem in explainability and search methods for finding future importance explanations, which is work done at UNC Chapel Hill with Hase and Mohit Bansal. Here's an outline of what we'll cover. Our first main contribution focuses on the out-of-distribution, or OOD, problem in explainability. We'll propose a solution to the problem and discuss experiments verifying the solution. Our second contribution is a new set of methods for obtaining future importance explanations, which we will show achieve state-of-the-art results on standard explanation metrics. For background, feature importance explanations take the form of scores attached to individual features, which are intended to represent how important that feature is to a model's output. In particular, we are interested in explanations for individual predictions from a single trained model. A common example of this is binary sentiment analysis, where feature importance explanations are intended to show what words or tokens are important to a model's overall sentiment prediction as positive or negative. Currently, there are many ways to give feature importance explanations. Of course, we want to know whether the selected features are actually important to the model's prediction. One standard way of doing this is to remove the selected features from the input and check that the model's predicted probability declines. We will call these edited points counterfactuals. De Jong et al. Described this as the comprehensiveness metric. Now, when it comes to how the features are removed from an input, there are a lot of different approaches that past works take. And this is where we see the OOD problem appear. Whether you delete words, replace tokens with a special token, or set features to 0, you are creating counterfactuals that do not appear in any standard training distribution. So these counterfactuals will be OOD to a trained model. But why is this a problem? Why can't counterfactuals be OOD to a model? There are many examples of past work expressing unease with the situation, and we summarize a few common reasons here. Models produce poor or insensible predictions on OOD data, or this practice leads to suboptimal attributions. We think that the most concrete reason expressed is from Hooker et al., who argue that when counterfactuals are OOD, it creates an ambiguity as to whether performance degradation is caused by the OOD-ness of counterfactuals or the fact that actually informative features are being removed from an input. We take this to mean that if the counterfactual wasn't OOD, then the model might have produced a different prediction, which shows less evidence of degradation. We think this is a good point, but at the same time, it seems like it does not apply when considering the degradation that a single trained model exhibits. When replacing features with, say, a mask token, then for a particular trained model, performance degradation has a single known cause. We replaced observed features with a mask token. There's no ambiguity about how replacing the features causes the change in the model output. To raise the question of what would have happened if the mask token wasn't OOD to the model is to ask, what would have happened if we had a different model, one which had a different training distribution that included mask tokens? So it seems like we need a stronger argument for not using OOD counterfactuals with a particular trained model. Our principal claim is that OOD counterfactuals yield socially misaligned explanations and explanation metrics. We say both explanations and their metrics because OOD counterfactuals are used to both evaluate explanations and to obtain them in the first place. Now, social alignment is a concept originating from Jacobi and Goldberg. What this means is that explanations communicate one kind of information to a person when they expected to receive a different kind of information. Here's an example from their paper. We could expect a feature importance explanation to represent evidence used to reach a decision. If instead the explanation shows as evidence selected after a decision was made, then we have a socially misaligned explanation. How does our argument play out in practice? We go through an illustrative example here. Suppose you're using BERT to classify the sentiment of individual words. We train this model with some label data and test on held out words. Let's say we compute comprehensiveness for a single word inputs to this model by replacing the word with a mask token. In this case, our baseline model prediction used in the comprehensiveness equation is simply that model's prediction for the mask token. Now, this prediction does not even depend on data. In fact, it will depend heavily on the model prior, regularization, random seed, and other training hyperparameters. We know this because we have ample evidence for neural models' sensitivity to these factors, and the mask token never appears in the standard training distribution. What is the problem here exactly? We suggest that People expect feature importance explanations to reflect what a model has learned from the data. People do not expect explanations to reflect the model prior or simply random factors. This diagram of the upstream causes of an explanation singles out these two factors, while other factors that people do expect an explanation to be influenced by are shaded in blue. So in our example, it's a problem that the explanation's comprehensiveness score would be determined by the model prior or random seed. For model classes like linear models, we would attribute the model prior to the model's designer. For neural networks, the prior has a complex and relatively unknown effect on the counterfactual prediction. We do not want these effects to determine what score our explanation gets. Instead, we want what the model has learned from the data to determine what score the explanation gets. Here, that means that the counterfactual prediction should reflect uncertainty in the label, as learned from the data distribution. Our solution to the OOD problem is fairly straightforward, that make the counterfactuals not OOD to the model, meaning train the model on the counterfactuals it will see at explanation time using a particular replace function. We call this counterfactual training, or CT. Since explanations can be expensive to produce with existing methods, in practice we use random explanations, which provides for a good objective function in theory. We find that these models take only a small hit to task accuracy, about 0.7 points on average across 6 datasets. The result is that the model predictions on counterfactual data will reflect what the model has learned from the data, as we expect them to. Then, the explanations and their metrics will be socially aligned. Next, we experimentally verify what we've discussed so far, and we address the basic question of which replace function you should use with counterfactual training. Our measure of OOD-ness is going to focus on distribution shift, as measured by a drop in a trained model's accuracy, which is a common choice of measurement. We evaluate the 5 replace functions shown here, which are often used in past work. We also experiment with both the standardly trained models and counterfactual trained models. In general, we use 10 seeds for every condition, meaning we test 10 different trained models and sets of explanations. We see that for models not trained with counterfactual training, the attention mask and mask token replace functions yield the least OOD counterfactuals, as they result in the least distribution shift. These results are for BERT with SSD2, but the trends hold with SNLI and Roberta too. Now, we look at the effect of counterfactual training on distribution shift, specifically with BERT with SNLI, and we see that compared to the results with standard models, counterfactual training produces a huge increase in model robustness, which follows directly from the fact that the counterfactuals are no longer out of distribution to the trained model. In fact, we see that using CT is much more important than the decision about which replace function to use, although there still may be a slight preference for avoiding the zero embedding function. In this experiment, we omit the marginalization method because it's far too expensive to use during training. So overall, we recommend that you use counterfactual training if you want to explain your model. Otherwise, the explanations you produce will be socially misaligned. Next, we assess several explanation methods using both standard and counterfactual trained models. Following DeYoung et al., we evaluate sufficiency and comprehensiveness at several different sparsity levels, meaning each explanation method must produce a set of explanations which vary in how many features they can select. We write this objective as so. For a function f, data point x, explanation set e, and sparsity level s, which is the fraction of features that can be selected. Here, s varies between 5% and 50% of the features to be removed for comprehensiveness or to be kept for sufficiency. Typically, people use salience methods to explain model behavior, which we use as a catch-all term for any method that outputs a scalar valued score for each feature in an input. We also want to consider search methods, which have worked well for combinatorial optimization problems in other domains. The salience methods we use include LIME, a vanilla gradient-based explanation, and integrated gradients. For search methods, we use anchors from Ribeiro et al., and we introduce a number of competing methods, including 2 gradient-based approaches, namely gradient search and Taylor search, as well as a couple of local search methods, which are ordered and parallel local search. We use a random search as a baseline for these methods. Now, note that we adapt all methods here to use the attention mask replace function, since it is a good replace function according to our prior experiments. One exception to this is with integrated gradients, where we use another good replace function, mask token, since this method requires interpolating between inputs in a way that doesn't make sense for attention masks. Importantly, we also control for the compute budget used by each method. We use up to 1,000 forward or backward passes in total per explanation, after which we usually start to see diminishing returns to increase compute. The one method we'll describe in greater detail here is parallel local search, or PLS, since it actually ends up doing the best. This is a very simple method that we propose. PLS searches neighboring states of a given sparsity level. These states are different attention masks in our case. If a new state is found that is better than the old state according to the current sufficiency or comprehensiveness metrics, then we adopt that state. Otherwise, we continue sampling new states until we find a better one or the budget is consumed. This new state sampling procedure is actually a random walk over the space, so it's possible we wander some distance in the space if all of the immediate neighbors have been checked before. So we compute sufficiency and comprehensiveness using standard and CT models, which are trained on 6 benchmark text classification datasets listed here. Now, 4 of these datasets include inputs that actually have a question and a document. Here, we never replace the question in these data points, since it's necessary to perform the task. As before, we trained 10 models with different random seeds for each dataset and model type, and now we use a subset of 500 test points for each dataset. We show the results for S and Li here, and we summarize trends from the table for all 6 datasets, which is in the full paper. First, we find that PLS is the best performing method on both metrics and model types, and this result holds for 21 of 24 comparisons across datasets at a p equals 0.5 statistical significance threshold. PLS can exhibit quite a large advantage over the next best method, depending on the setting, with up to a 17.6 point improvement. Second, we note that Lime is the best salience method, but it is the best overall method only once out of the 24 settings, and it's actually outperformed by a random search 9 out of 10 times on sufficiency. Third, we notice that the metrics are often much worse for CT models than standard models, in fact, by up to 24 points. Since the difference between these conditions is that the counterfactuals used in these metrics are OOD with standard models, this tells us that these common metrics are inflated for standardly trained models, but are not inflated for the CT models. Finally, we want to highlight a few takeaways and subtleties to these results. Most importantly, we suggest that if you want to explain your model, you should train it with counterfactual training. We've been asked before whether we should use CT models if they're harder to explain. We want to emphasize that explanation metrics are worse for CT models because they are socially aligned. This is what we want. We want explanations to communicate what a model has learned, rather than what the model prior or random seed influences them to be. At the same time, we need to give a word of caution. Counterfactual training with current neural models is not guaranteed to eliminate the influence of the model prior or random seed. We have plenty of evidence that these factors influence model behavior, even on in-distribution data. But we can at least get explanations to reflect what a model has learned from the data at all. In general, we observe that search methods provide a new state of the art on common sufficiency and comprehensiveness metrics for future importance explanations. We recommend that those interested in obtaining high-quality explanations use search methods over existing salience methods or other heuristics for obtaining model explanations. Lastly, we just want to emphasize that it is critical to control for the compute budget available in these experiments. We noticed it is very rare for papers to discuss the compute budgets they use in experiments, but we find that results vary substantially with the compute budget. In some settings, we see performance increasing beyond 1,000 queries to the model, so even more compute may be beneficial. Going forward, it will be necessary for researchers to develop methods that use an appropriate amount of compute depending on the use case they envision for their explanations. Are explanations needed instantly, without any latency? Do we have seconds, minutes, or days to get an explanation for a decision? It will be helpful to design and evaluate methods with these constraints in mind. Okay, thank you. And that is it for our presentation. The code for our paper is available on GitHub, including a demo of PLS in action, part of which is shown here. please feel free to contact me, info shown here, with any questions or comments. Thank you.